Please welcome to the stage MIT Alumni Association CEO, Whitney Espich.
Welcome. Good morning, everyone. Really great to see you all. It's wonderful to be sharing the same space with so many of you. Did you see what I did there? Space. That's our theme. Let's get with it, yes? All right. Wonderful to be sharing the same space with so many of you. As nice as it is to be in person, when we needed to be remote over the last few years, MIT navigated that better than most. And we're sticking with it. Right now, alumni around the world are with us via streaming. Let's say hello to all of this great gathering of alumni around the world who are on video, on streaming with us. Yes? Awesome. All right, well, today we're going to take bridging distance between in-person and remote to a new level. I can neither confirm nor deny that we will hear from some fellow alums who have a message for this very audience as an example of remote communication, super remote communication. So think about that. Perhaps the ultimate in hybrid events will be happening today. Consider that a hint, but I'm getting ahead of myself. MIT's been leading the way in exploring space far above our heads for generations. The effort we're probably most well known for is the Apollo mission, MIT having been instrumental in creating technologies that helped the moonshot to hit its mark at the end of the 1960s. Though that is the best known example, it is by no means the only one. It's not an exaggeration to say that MIT alumni have been core to the human exploration of space, not only helping astronauts get to the surface of the moon, but also discovering the pulverized nature of the particles beneath its surface. And our alumni have even helped us see dramatically, exponentially farther than the moon, out into the deep recesses of space, searching for other forms of intelligent life. That's a long way to look up and look out. But let me also remind us to look in the other direction as well, back on our blue planet. Imagine that you're all on the International Space Station now, casting your eyes down at Earth. What would our world look like if every MIT alum was a tiny point of light? You would see that MIT alumni have spread yourselves across the globe, doing important work in virtually every field, from technology to innovation, to academia, to the arts, to nonprofits, government service, and more. That's all of you. Today, you are going to hear from 5 of our stellar faculty. Check your electronic programs for details, as well as our moderator, Vice President for Research, E.A. Griswold, Professor of Geophysics in EAPS, current co-chair for the President's Council of Advisors on Science and Technology, Maria Zuber. There will be a break after our first session, and then, for the second year, the presentation of the MIT Alumni Better World Service Awards. Then Vice President Zuber will return to moderate our next session on space. And finally, MIT President Sally Kornbluth and MIT Alumni Association President Steve Baker will sit down for a fireside chat. Our speakers will take you far out into space and back here to Cambridge. That sounds like a lot of fun, so let's get started. Some quick housekeeping about the space-related panels. Audience members, both in this room and online, are encouraged to submit your questions during the faculty Q&A portion of Tech Day. For those of you who are watching online, simply input your questions in the chat box below the live stream video on the webpage. For our audience members here in person, using your smartphone camera, point your smartphone at the QR code that appears on the screen right here, and tap the link that appears or type in the link that is displayed. This will bring you to a web page where you can submit your questions. These will be visible on the screen throughout the faculty Q&A periods. If you are having trouble scanning the code, MIT Alumni Association staff are also located throughout the auditorium and can assist with your QR code. Please know that due to time constraints, scheduling, you all want to get through this and get to lunch. We may not be able to answer all questions, but we will do our best to cover all the themes. Thank you so much for being here. And now, to the stars.
Please welcome to the stage MIT Associate Professor Kerri Cahoy.
Good morning, everyone, and welcome. excited to be here today to talk about revolutionary nanosatellite technology. On this slide, you'll see 2 CubeSats, nanosatellites. They're 5 kilograms each. On the left, we have a weather sensor that's used to sense tropical storms and hurricanes on a mission called Tropics. And on the right is a MIT student-built laser communications satellite that is to help get data from orbit on these tiny platforms down to the ground. It is called CLIC. It's part of a 3-satellite mission, CLIC A, B, and C. This is CLIC A. So I'm excited to talk to you about more of them. So these nanosatellites have some really important advantages. They don't have to be only on the rocket by themselves. So they let you do ride shares. So you can have multiple spacecraft on a rocket, and you can get up to space in a couple different ways. One way is kind of like packing your bags and going to the airport. You go up as cargo to the International Space Station, where the astronauts will unpack you, put you on a robotic arm, and then, just like shown in the slide here, eject you into orbit. These are 2 MIT satellites. The one I'm talking today is the LaserCom one, CLIC A. Also, hot off the press, or hot off the launch pad, this past month we've seen 2 MIT Lincoln and MIT student-developed missions for weather sensors. This is the Tropics mission. They are launching on a new small satellite launch rocket called the Rocket Lab Electron from New Zealand. 2 of them went up on May 7th, and then another 2 went up on May 25th. I'm going to talk a little bit about what those missions are doing and some of the previous precursor successes that we've had on the experiments leading up to those. So first, the Tropics mission. This is a nanosatellite mission that is to help us do a better job of mapping where hurricanes and tropical storms go. It's very difficult to be able to track these because the satellites that we have, the weather satellites that we have on orbit right now, revisit the same spot not even every day. Sometimes every couple days, sometimes every few days. What we can do when we have more smaller satellites is put them into orbits with more of them up, so we can get revisits rates as low as only an hour. So when we have situations like this, where this is an example of Hurricane Ida, we can actually be able to improve this cone of uncertainty from where the hurricane is. So this is the predicted path, which is pretty wide, and it's hard to allocate resources and get the resources we need both for prevention and for recovery. But if we knew the actual track, which is this line, better, we could do a better job of that. So these missions let us do that by sensing with radio frequency antennas. They sense the emission from atoms and molecules in the atmosphere. They're vibrating, and they give off these emission signals. And you can measure them just like on a radio station, kind of tuned to different channels. These antennas listen to different channels of radio frequency energy, and each channel lets us see a different height in the atmosphere. So this is an example of one of the channels from some of our on-orbit data. This is Hurricane Ida coming in. This is before landfall, and this is after landfall. And this is looking at one of the channels that does a really good job of picking up precipitation, scattering off of precipitation. And you can see that before landfall, these are the rain bands, and after landfall, these are where the rain bands are. So you can use this data to feed into our numerical weather forecasting software, which is only as good as the data that go into it, to improve the storm tracks and the predictions. It's really important as things get more intense. And to just give a sense of how small these are compared to the other satellites that don't have as many revisits, this is the kind of state-of-the-art weather satellite, SWOMI NPP. This is a human in a bunny suit down on the lab floor here working with it. This is 2,100 kilograms. For comparison, this is the nanosatellite. It's 5 kilograms, and this is kind of to scale, so it's about as long as your arm. So this is very exciting work. However, one of the hard parts about these nanosatellites is getting data from them to the ground. They don't have any big antennas on them. They don't have any huge batteries. They don't have huge solar panels to get that data down. And even if they did, the radio frequency spectrum for getting data from space to Earth is really congested. It's really contentious, and it's difficult to get licenses for those. So what we are doing here at MIT, and this year our students have developed a way to use essentially just like this laser pointer from space to blink it kind of on and off to get data down to low-cost ground telescopes, literally on campus. So we built a satellite called CLIC-A that I'm going to talk about. That was the one deploying from the space station, and it connected to an amateur astronomy class telescope that you can literally buy on Amazon with, it's souped up a little bit. And we had a successful data link to the telescope that I'll show you about. And our next step is going to do a cross-link between terminals on orbit, and that's coming up next year. So this is the ground station. It doesn't look like you would expect. So literally, during the pandemic, everybody was building sheds in their backyard. We built a shed, too. So this is at Wallace Observatory in Westford, and the roof on it kind of slides over to the side, and this is where we have the 28-centimeter amateur astronomy Celestron telescope that has some extra, extra accessories for tracking and being able to track the satellite. And this is kind of a comparison of the state-of-the-art facility. So this is an amazing facility where they do an amazing amount of work with deep space laser comm missions, but it's much bigger. So this is a telescope at Table Mountain in California, and this is kind of the comparison to the inside of the shed. We have a lot of racks of equipment, a lot of optical elements, a lot of adaptive optics. So this is the data that we took in November, just when it was getting cold. We need to plan it for summer next time. But this is light from that little satellite coming to the telescope at Westford, and this is showing that it does it with pointing error that's low enough to meet our goal line to be able to communicate at 10 megabit per second data rates to the satellite. So we're very excited about this work. Just moving towards future forecasting, a lot of exciting things are happening in the space domain. We are moving towards more of a space internet. I think we'll start to see analysis happening more on orbit. So all of the data that these satellites are taking, we do have a struggle right now to get them down to the ground and analyzed. I think with AI, with onboard computing and processing improving, and better resources being made on satellites, we'll start to see these data being exchanged above the clouds and being able to instead network and develop a space internet where we're starting to do more of this analysis on orbit. And our results, the inferences, the lower data rate things are what we'll need to send to the ground. So we'll be able to pass data around, do the inferences analysis on orbit, and then have a reduced data volume to the ground with more nodes on orbit doing more persistent, constant imaging and getting better data. So this is all very exciting, and we're trying to build the technologies to make that possible. MIT is really excited about leading the way in this area. We have a new small satellite collaborative that brings together multiple departments on campus, a lot of our affiliates along with us. And so we're going to innovate and lead the way. And I don't know if you noticed, I hope you noticed, on top of Building 54 this year as you visit campus, we have managed to refurbish the radomes thanks to ARDC and other sponsors. So we have a new radome up on Building 54 for the 5-meter dish up there that we are going to use for both amateur radio activities as well as small satellite mission and communication. So it's all very exciting, and I'm happy to talk more about it and help get everyone connected and involved. So thank you so much, and appreciate the time.
Please welcome to the stage MIT Assistant Professor Danielle Wood.
Good morning to my fellow alum. It's so great to see you all. Thanks for being here. Hello, I am Danielle Wood, and I'm so excited to talk to you about my space-enabled research group, where we design systems, such as propulsion systems for satellites with beeswax, that are asking how we can promote sustainability on Earth and in space. One of the things I love about MIT is that we do important traditional things in non-traditional ways. I was very excited recently to see an MIT news story that features some of my leadership. We have recently announced the first time we're having graduates in a formal major in African and African diaspora studies. I have the honor of serving as the faculty advisor to students like Stacy, who are graduating with this major or minor or concentration in the humanities. Now, you may be wondering why a professor in the Media Lab and Aeroastro is the faculty lead for African Studies at MIT, and why I co-teach a class in African Studies along with Professor Fox-Sorrell, Michelle DeGraff, and here's why. I am an expert in the activities and the collaboration with countries all over Africa who want to use space technology to promote sustainability right here at home. You just saw a wonderful talk about the kinds of small satellite technology that's available these days. And since the 90s, countries all over Africa have been exploring how to use these tools for their own sustainability. When I was an undergrad here at MIT, I was interested in the question of how to get involved with development projects in Africa. I used to go to Kenya and to volunteer at a school. But here at MIT, I was working on the Spheres robots that were headed to the space station and thinking, is there a connection between my interest in African development and my interest in space? I wanted to work for NASA and be part of that mission. And soon I learned that countries like Kenya, South Africa, Ghana, and others have space programs. Many of them are focused on using satellite data to make better maps at home. But also, as technology was getting more and more affordable, they were very interested in using small satellites to train local engineers and be a part of this small satellite revolution you're just hearing about. So these days, I'm both interested in designing next-generation small satellite technology, but also collaborating with the countries that are creating their own domestic space programs. They're also interested in the question, how can they support progress on sustainable development goals? How many of you have seen this graph before? Do you know the SDGs? That's wonderful to see. If you don't know them, please go look them up and figure out which ones you are working on. Because the global community is engaged in an urgent mission to ensure that we are addressing our important challenges of our generation. We need to eliminate extreme poverty. It can be done. We need to coordinate on making sure everyone has access to food and water, education, opportunities for jobs. And this is something that everything can support, including our space technology. One of my areas is asking, how can we use the wonderful data from satellites, such as those operated by NASA's Earth observation systems? They take measurements of what's happening in the atmosphere, in the poles, where the global important ice loads are being held, in the ocean, in forests. There are many special kinds of data, and to be honest, it's wonderful free data, but it is hard to use. I have wonderful, highly trained students on my team, and we take a long time learning each different kind of satellite. And that means that it's a barrier for important leaders at local and national scales who are asking how they can use this data in their own countries. I often work with NASA. Recently, I received a grant from NASA as part of their Applied Sciences program. We're asking how we can make it easier and reduce the barriers for countries like Angola to use NASA satellite data. I want to give a shout out to Professor Dara Ntakabi here at MIT. He's an expert on drought decision-making, especially using satellite from NASA's SMAP data. Southern Angola is a region that faces chronic patterns of drought and floods. Local communities depend heavily on rainfall to keep their crops and animals healthy. I recently visited Angola and have been invited by their National Space Agency to work on a several-year project to apply NASA satellite data to improve their use of the mapping and decision-making during drought response. Now, they're a country that's investing in having their own space program because they believe it'll help with communications as well as these important mapping issues. And NASA provides free data that's very relevant, but of course it takes expertise to learn how to turn the NASA data into action. One of the ways we can do it is by making maps like these that show patterns based on the soil moisture. And the soil moisture can be estimated by measuring the microwave radiation from the Earth. And we're turning that into maps showing where the drought is extreme. Eventually, we'll also overlay that data with socioeconomic data and help to direct where is there the greatest need for drought response. Another example is in Ghana. They have an exciting space program called the Ghana Space Science and Technology Institute. They're also interested in radio astronomy. What you see here is the first example of the Square Kilometer Array Telescope. It's going to be a multi-continent radio telescope happening in several countries in Africa and Australia, studying the ancient history of the universe. Back here on Earth, Ghana is also concerned with how to use satellite data to track important issues like deforestation due to both legal and illegal mining. A publication we talked about recently with NASA funding highlights techniques to use NASA satellite data to identify areas where there's environmental hazards due to illegal mining in Ghana. We're doing this in collaboration with their national space program. In fact, I'm heading to Ghana later this summer, and we'll have a chance to review and see how our NASA satellite data estimates compare to local findings. Now, there's a major concern with illegal mining in Ghana. There are regions where it's pursued, especially for gold mining, in methods that do not follow the local environmental protection requirements. It leads to water pollution and, of course, deforestation at rates that are not approved. And this is an important area where biodiversity is key to preserve. We can use a combination of optical data, things that our eyes would interpret, but also three-dimensional information through LiDAR and radar measurements to estimate what kinds of mining are happening and where it's changing. Our data shows that there's an extreme amount of deforestation due to this artisanal mining, in particular that the artisanal mining is increasing its rate faster than the legally approved mining. And we can tell this based on the patterns of the mines and the land change that's happening. We also created then a map looking at the whole country based on satellite data using some machine learning to interpret the information. And we're able to make maps showing where land use is changing, where you see a change between urbanization, deforestation, agriculture. All of this is so important because the government of Ghana is dedicated to the Sustainable Development Goals. They're eager to have information to report how things are changing and to make better policies to improve life for their country. When I go there, I'm working with the Statistical Service as well, and they literally, as you see, have the poster for the SDGs, but they're the ones who are collecting all the important data to track their progress for these important goals. And we're dedicated to transferring the knowledge between our teams. They are experts on what's happening locally, and we're providing this data from satellites. Together, we can help them figure out how to make the best policies toward development. So we're so happy to share this example, and I hope that you find ways to use your technology to support the SDGs as well. Thank you so much.
Please welcome to the stage MIT Professor Jeff Hoffman.
Hi everyone, welcome back. So before I came to MIT, now 22 years ago, I spent 20 years with NASA as an astronaut, made 5 flights on the space shuttle. One of the things that never ceased to impress us was looking back here at this very thin blue line. You know, on a beautiful sunny day, not like today, it looks like the sky, blue sky goes on forever. No, it's this tiny little thin thread of blue that protects us from the harsh environment of space and, of course, keeps us alive. And this is the problem when you go into space, whether you are in orbit around the Earth or on the moon, or someday going to Mars. I hope you've all seen the movie. We need oxygen to breathe. And Matt Damon managed to get back to launch himself into space. That was, a pretty cool movie. What they didn't tell you about in the movie, though, where did all that propellant come for this rocket? Hey, we're Aeroastro. We know how to calculate these things. I don't have time to lead you through the whole calculation. I'll just put up the results there. But, we know the gravity is less than Earth, doesn't have quite so much atmosphere, 80% propellant fraction, methane, oxygen, propellant. You're left with 30 tons. We breathe, a little less than 1 kilogram of oxygen per day, and that's what most people think of. Why do you need oxygen in space? Yeah, if I were on Mars, I'd want oxygen to breathe, okay? But if I want to come back home, I need a heck of a lot more oxygen. And here's the problem. Again, in Aeroastro, we can calculate what we call the gear ratio. To get 1 ton of anything on the surface of Mars, we've got to put 15 tons in orbit around the Earth. Now, a lot of stuff we have to send to Mars. Anything we manufacture, spacesuits, computers, habitats, we don't make those things on Mars, at least not yet. Dumb old oxygen? I mean, it's expensive to send stuff to Mars. And if we could make oxygen on Mars, we're way ahead of the game. And so this is what I hope we'll see someday in the future. We'll send people to Mars, but we want to bring them back. And what I've just shown you is the problem. It's expensive to send things there, especially oxygen. So ISRU, which is in situ resource utilization, hopefully will provide part of the answer. This is what our MOXIE experiment is all about, the Mars Oxygen ISRU experiment. This is a full-size 3D printed, just to give you a sense of the scale. This is the actual instrument. You've all electrolyzed water in high school chemistry, right? Well, you can electrolyze carbon dioxide, and although Mars has a very thin atmosphere, 1% the density of Earth at sea level, it's almost entirely carbon dioxide, 95, 96%. So we take the carbon dioxide, we pull it in through a HEPA filter to filter out the dust, we compress it with the scroll compressor up there and put it into an electrolysis unit, solid oxide. It's hard to electrolyze carbon dioxide. You have to heat it up to 800 Celsius, then you pass it over a cathode with nickel and some rare earth elements, and then you have to run it through a special ceramic electrolyte with scandium-doped zirconia, which has a crystalline structure that only allows oxygen ions to penetrate, not electrons. So we end up getting basically 100% pure oxygen at the anode. And this is something that has been tested many times in a laboratory, but NASA has a rule that if you have a critical process or piece of equipment, and making oxygen for a trip to Mars, I would say, is pretty critical. You've got to test it first in the real environment, and that's why we had to send it to Mars. So here we are loading MOXIE onto the Perseverance rover. It doesn't look much like a rover here. It's upside down. It doesn't have the wheels yet, but that's what a rover looks like in its infancy. Then we launch it to Mars. We land it. Perseverance landed back in February of 2021. It's a remarkable mission for many ways, not just because of MOXIE, and it's making a lot of firsts. On the business end of the robotic arm, in addition to scientific instruments like X-ray spectrometers, there's also a coring device which is, for the first time, collecting samples that we'll be able to bring back to the Earth, because one of the main purposes of this mission is to look for potential evidence of past life on Mars, which is why we went to Jezero Crater. You can see this, the river, and it set out a delta. Clays and carbonates, at least here on Earth, are excellent materials for preserving fossils. Now, we don't know if there was life. If there was, did it leave fossils? If there are fossils, you still have to be pretty lucky to find it. But we're trying, and now we have deposited 10 sample canisters. They're lying on the surface of Mars, waiting to be picked up by a NASA European Mars sample return mission, and we'll get them back sometime, hopefully in the 2030s. And in Earth laboratories, we have instruments powerful enough that if there are fossils or any chemical signs of life, we'll be able to detect it. The other incredible thing, I'm sure you've seen pictures, but back on April 19th of 2021, we had the first flight of a aerodynamic vehicle. This was a Wright brothers moment. It only made a simple flight. It went up 5 meters and came back down, but it was the first controlled flight of an aerodynamic vehicle in the atmosphere of another planet, like the Wright brothers. On the 100th anniversary of the Wright Flyer, they put a model up on the top of the dome. I don't know if they're going to put a model of the Ingenuity helicopter, but it certainly deserves it. And the very next day, on the 20th of April, for the very first time, oxygen was produced on another planet from local resources. I'm sorry, oxygen is not as photogenic as a helicopter. You can't see it. All I can show you is but we did it. And what we set out to do was to demonstrate that this process would work during any season and at different times of day. The sort of shaded area is the predicted density profile in the course of a Mars year. We've been running now for over 2 years. We've run 14 times. This is kind of and we're due to run next Tuesday again, and we're going to try to push our production up to 12 grams an hour. If we could do that continuously, which we can't because we use more power than than the rover can generate with its RTG, and so we would run down the batteries. But if we could produce it continuously, we could keep a small dog alive. That's not what we want to do. Ultimately, we want to keep people alive on Mars, and so the people that, the company out in Salt Lake City that has made the electrolysis unit already is working with NASA to produce a human scale. Instead of producing 10 to 12 grams an hour, in order to produce enough oxygen to get that 30 tons during the time between missions, you have about maybe a year and a half to do that. You have to produce about 3 kilograms an hour. So we're talking about scaling up MOXIE by several hundred, but we can do it. And so someday, I don't know when it's going to happen, we will send people to Mars. What's it going to take to do that? Well, what's really holding us back is that Mars is a long way away. You know, the moon you can get to in a couple of days. Mars takes many months. So the things you want to be on the lookout for, so you'll know we're actually ready to go, is first of all, if we can get there faster. NASA's working with the Energy Department on nuclear thermal propulsion. And if we could get there faster, we'd really, really be ahead of the game, because one of the problems is during that whole trip of 7 or 8 months, you're exposed to cosmic radiation, you have to have logistic supplies to eat, and so on. So getting there faster is really going to be important. The other thing to keep your eye on is how successful are we at going back once again to explore the moon, but this time, remember, NASA doesn't have an Apollo budget. And so this is the big challenge for human space exploration, is how do we explore and not have a NASA budget, not have an Apollo budget. And that's why being able to use local resources is so important. So I don't know who the people will be who first go to Mars or when they're going to go, but my advice to them, and I hope they won't forget, don't forget your MOXIE. Thank you.
Please welcome to the stage MIT Vice President for Research, Maria Zuber.
All right, good morning, everybody. It's so wonderful to see you all here. So I'd like to, first of all, just start off with thanking all the alumni online and here in the auditorium for upvoting space as this year's topic, because it's my favorite thing. And so I'm so thrilled to be with you today. So what we were trying to do when we put this program together for this event was to try to convey to all of you the many skills and talents that you need to really explore space, utilize space, and exist in space. And it's not just you go to the Aeroastro department or you go to the physics department, that you really need engineering, you need science, but you also need things like governance, national security. There are many things that come into it, and we were trying to get give you a feel for many of those things. So we're going to have some conversations today. We want to hear from you, and I'm not going to spend any time up at the podium talking here. I want to bring our first set of speakers up, and we'll get the questions going. So. Okay, all right. So Kerri, let's start with you. And so I was telling all of our guests here in attendance and online about the very many skills that we need to explore space. And you are a professor in Aeroastro, and you're also a professor in Earth atmospheric and planetary sciences. And in your talk, you showed your small satellites, and then you showed the observations that they're making. And you're an end-to-end person. I mean, you buy the components, put them together, test them, send them up there, bring the data down, analyze the data, talk about what it brings to really have a grasp of the end-to-end process in terms of the quality of the hardware, but also the scientific outcome.
Yeah, it takes a village to have a space mission, as we know. It really takes everything. It takes electrical engineers to do the component development and testing, as well as computer science to write the software, mechanical engineering to do the CAD work, and then order the parts and help put it together and test it and make sure it'll survive launch. Environmental testing, everything. And then most importantly is the interaction with the scientists, because you're doing this all for a reason. So you need really good requirements developed. You need to talk to the scientists to understand what the data is that they're hoping to get and how the instrument you're building is going to get that data for them in a way that's usable for them and is getting it at the right time and in the right place. So having the ability on campus to work across departments from AeroAstro and to be able to bring in students, both graduates and undergraduates from both the School of Science, the School of Engineering, and now computing to work on these projects is really necessary. We need all of them to do a good job, and having students who get to participate in that process makes more people who know how to see everything and put it all together, so they'll be able to go out into industry, into research, to NASA, and continue to do this and grow the crowd of people who can help bring these things together and see all the parts that it takes and work together. So it's really a great opportunity to be here, especially with our students and our alumni and our affiliates, to be able to work with everyone to make these things happen. It's just amazing.
Great, thank you. So I have a couple more questions I'm going to ask here, but again, I want to emphasize, let's get your questions in. If you're streaming in, input your questions into the Sligo area beneath the streaming. And then if you're here in person, scan the QR code and it'll show you how to put your questions in. Okay? Danielle, okay? There's been a lot of talk about the democratization of space, okay? Space used to be the place of former test pilots, okay? Now space is becoming a place for everybody, and you showed some really excellent examples of how space can be used to help all kinds of people on Earth. But on the other hand, access to space, the commercialization to space, it's basically tech billionaires, okay, that are driving the effort. And what do we do to get more regular people, like us, for example, up into space, and like all of you here? So,
thank you for the question. I think a lot of news media tells one story, that we see a few people who appear to be the ones driving what's in space. But I want to share, I'm flying tonight to Vienna, which is an important hub, actually, for the global space conversation. I'm going to Vienna, Austria, because there's an office there called the Office of Outer Space Affairs in the United Nations. And on the next week, I'll spend 5 days with delegates from countries around the world, from every continent, and they are talking about the global issues of space policy for the coming years. It means countries from Africa and Latin America and Asia, every region, are saying what is important, including reducing space debris to make sure it's safe for all of us to keep operating. This is a really key issue. And asking the question, who gets to play a role, not just in human spaceflight, but in every form. I think it's so important that all the areas of space technology are well attended by people around the world. It means researchers from every college around the world sending experiments to space stations in the future to understand microgravity better. It means people getting involved with activities. For example, my team leads the Zero Robotics program, inherited from Professor David Miller in AeroAstro, a lot of good support from Jeff in the past. This means we have students all over the world involved with learning to code a robot that's on the space station, where they get to see, at the end of the summer of training, they get to see an astronaut saying, this is your code, and now we're going to push the button, and your robot's going to do what your code says, and hopefully we'll see that it works well. So I think we see a lot of ways that humans can engage with space, both through remote participation, like sending your code up, through being able to have your science done, through sending microgravity research experiments. My hope is that every university in the future has opportunities to engage with these various forms, whether it's science, microgravity studies, engineering. I think that's something we can really scale right now. And the United Nations plays a key role in that as well.
Great. Jeff, you've flown in space 5 times, and now you've just been the first person to, leader of a team that has created a prototype for rocket fuel on the surface of Mars. How do those experiences compare? I mean, you would have thought, how do you follow walking 5 times and go to space 5 times? And
Well, you know, when I first went to NASA as a young astronaut in 1978, it was just a few years after the Apollo program, and we all thought that we were going to get to Mars. I mean, all it was going to take was another president to say, yeah, let's go to Mars, and it will happen like it did in Apollo. The real world has sort of caught up with us. As I said, NASA no longer has an Apollo budget, and I've been very fortunate. That one of the reasons I wanted to come here to MIT, I was sort of concerned when I left the astronaut corps. You know, I love space. It's been my life, you know, am I going to lose my contact with it? And this has been the wonderful thing here at MIT is, you know, I've had so many research projects with NASA, this being one of the most significant. So I've been very fortunate to have been able to continue to make contributions to human space flight, even while recognizing that I've probably had my last flight, you know, back in 1996. Although if there was ever a chance, I mean, I'd be happy to go again. Don't tell my wife, please.
and it's becoming possible. Okay, so we've got a bunch of questions from the alums here, so let's start out with them. What issues do you see going forward with all of these small satellites being put in orbit over the past several years? Kerri talked about the congestion of the communication frequencies. What are the other issues? Kerri, you can start out, but I think Danielle probably has something to say about this as well.
Sounds good. Yeah, so there are a couple of issues. Obviously, there's the radio frequency congestion, there's the space debris problem, there's light pollution for astronomy and astronomical telescopes. All of these things are definitely concerning. A lot of the CubeSats and nanosatellites, like the ones that I work on for test and demonstration, are deployed at altitudes where, you know, they, for example, our missions are deployed in September. By March, they're burning up and they're little, you know, they've completed their mission and now they're meteors. So a lot of the testing and demonstration can be done at lower altitudes, and that's a good, responsible way to take care of not leaving debris in orbit. Beyond that, there are a lot of other missions where you need to have this, there needs to be some type of regulation that makes it part of your mission plan to responsibly deorbit, and these have been consistently updated. So those are some of the things that we need to think about. If you don't have propulsion on board or thrusters on board, then you need to have some type of device, if you're low enough, that can create enough drag to bring you down eventually. And if you're high enough, then we have more problems. Like, for example, in geostationary orbit, there's what's called a graveyard orbit. That's a couple of 100 kilometers above, where it's just like if you're in geostationary orbit, you're, you know, 35,000 kilometers up, you're not going to have enough propulsion to come back down. So they've been leaving things up there, and at some point those will go unstable and have like crossing orbits that'll be an issue. So we've got a cleanup task on the decade-level horizon, and I'll hand it over to Danielle to comment on how we're going to solve that problem.
I love it, Kerri. Thank you so much. That was perfect, actually, because what you've highlighted is actually a wonderful motivation for excellent research. I want to appreciate Professor Rich Linares, Professor Morba Zhao is visiting faculty with us. What we really need to address these issues is a globally adopted system of space traffic management. This is one of the research areas. As somebody who wants to make sure that every country in Africa can have their own space program and not be distracted by these key issues, we need to now move into a future vision. It's a research area. It's questions on how do we track everything that's actually orbiting the Earth? That's still an ongoing challenge. How do we then think about this upcoming system? We're going to eventually retire the space station, and we'll see a number of new private or internationally coordinated space stations that are smaller and operating with humans and non-human systems. How do we make sure that there's information being shared across countries and across systems? The US is playing a key role, but it needs to be a global effort. So there's some really interesting research. I have students who are taking pieces of these problems and asking, what is the role of the US military, for example, as we address upcoming ways of doing servicing in places like where you mentioned GEO. Meanwhile, my team is trying a simple question, not simple, but a small piece, which is how do we increase the use of propulsion for these smaller satellites? That's where I mentioned earlier. It would be great if they were sustainable materials. So we're studying candle wax and beeswax as candidates. But there's a lot of fun innovation because these problems are so dire. We want to make sure it continues to be feasible for every country to safely operate in space. So we need to invent a new space traffic management system with all these components.
Okay. All right. The next question, I think, is going to be for all three of you. So all three of you significantly involve students in your research, okay? And as students actually building hardware, analyzing data that it comes down. Talk about the role of students being able to do things that kind of have to work, okay? And the level of training and the level of discipline that they have to be able to develop. I mean, they still need to fail in the lab, but if you're spending a lot of money to spend something into space, it's a big effort, and so there are real contrasts in this. And I wonder if you could all comment on your philosophy of how you handle the need to educate and the desire, but the desire to succeed more often than not. So Jeff, do you want to start things off for us?
Yeah, I mean, people often ask, why do we spend so much money testing things in the space program? And the reason, I mean, I think it's obvious to everyone here, once you've launched it, I mean, yeah, I went up and I fixed the Hubble Space Telescope back in '93, but that's an unusual opportunity. Normally, once you launch something, it's up there, and that's not where you want to find out where the failure modes are. You want to put all of your hardware through as rigorous a test as you possibly can, and somehow teaching students to think, how can things fail? I mean, that was what I had to do as an astronaut. One of my important jobs, look at a piece of equipment. How can this fail? And if it fails, is there anything we can do about it? And what sort of testing do we have to do to make sure that it won't fail? It's a kind of a psychology which, if you're going to be successful in space research, you have to internalize it. Test and test and test. And this is why we have students working in the labs. They do analysis. How far can you push something before it's going to fail? Then go into the lab and test your analysis. Make sure that you've done it correctly. And by the time they finish working on a project, and also there's something for a student to be able to put their hands on something that they know is going to be up in space. That's really exciting, and that's an opportunity to get them thinking of, what do we have to do to get it to work.
Great.
That's enough for me. I'll pass it
Danielle.
on.
To be honest, part of the answer is that we teach students to experience failure and then to be able to recover from it. My most recent failure is a fun story. I really want to appreciate one of our undergraduates. I want to appreciate Denuri, who's been working with me for the last 3 years in Air Astro. She got an award this year because she has played a key role in an experiment we were trying to send to the moon on a rover with United Arab Emirates inside a lander with Japan, launched by a US rocket. It was going to be, hopefully, the first commercial system to land safely on the moon. If you were watching some of the recent coverage, you might have seen that we crashed. We did not succeed. But I'm so proud that first, an undergrad had a chance to build a special part of our experiment. It was a passive system to collect dust on the rover wheel. And I was excited to say, here's my student who did the final packaging and testing of this system that she manufactured as part of our design, and it was on its way to the moon. As soon as it crashed, she built another one that we then sent for follow-up testing in the lab, because we wanted to compare our expectations to the lab. So I think she has now experienced both building something that she could say, yes, this is on its way to space, and she learned how to do the experience of, it didn't go as we planned. Let me quickly do some new change of plans and more engineering to still keep going and still not give up. So I think part of it is learning how to recover from failure. Failures do happen, but we're going to keep going.
Great. Kerri?
Yeah, I guess just really quickly, two things. One is planning margin, both in, if possible, and I say this like laughing because we're always short on time for software testing, but planning margin in schedule and in budget so that when these things happen, there's time for them. Being really responsible in reporting when things aren't going well. And being honest and having a good relationship with the students so they're comfortable telling you when this is too much or this isn't going well or we're worried about this, and being able to hear from your team. A lot of the social engineering skills are really important in being successful. Realizing that failure is something you have to deal with too. Like it'll be okay. Part of it is to just really enjoy the journey, enjoy the skills you're gaining, enjoy the people you're working with, and keep pushing that vision forward through adversity. It's the through adversity part that I think really mints the teams that come out of space experimentation. Is you get there, and if you don't get there, you'll go again. And that's I think part of the process and one of the more important parts of things that students learn and benefit from.
So we've got a variety of technology-related questions, and Kerri, there was one on the role of atmospheric disturbances in getting laser comm signals down to Earth. So maybe you could comment on that.
Yeah. There's always the question about laser comm. Oh, but the clouds or the atmosphere, and it's true. You can't, at least not with the low power lasers, send them through clouds and atmosphere. And you do need to be able to. When light is coming through media that is varying, it refracts, right? And so it disperses, and so the signal that you get down isn't this nice, clean wavefront. A lot of what we do is correct for that, and there are active optical elements, mirrors that you can use that you actually measure the amount of distortion that is in the signal, and then apply nanometer scale mirror change. You bounce a signal off a mirror with a surface change, and then you can correct it and re-steer the beam where you want to have it go. So there are technical solutions, and then there are kind of operational solutions to dealing with that, meaning that you might want to route your signals on orbit to a place where downlinks you have a clearer atmosphere environment to downlink them. But there are some great technologies with mirrors and what's called adaptive optics controls to try to help correct for the effects of turbulence and the atmosphere on optical signals.
Okay. Danielle, are there particular technological advances that have, I'd say, accelerated this opening up of space to try to help people who need help on Earth?
Thank you so much for asking. I didn't have time earlier to talk about the fun ways we get to use AI. So earlier I quickly said, well, we made a whole map of Ghana and talked about all the land use change. When I say that, what I mean is I'm collaborating with teams that are asking what's the best way to use machine learning to interpret information as we look at satellite data from multiple kinds of satellites and understand exactly where do you classify an area as a city, maybe it's a forest, maybe a certain kind of crop. And so it's exciting to see that there's both increasing open access to both not just the data itself, but to cloud-based data processing. I can think about companies like Google and others, and also NASA's asking their questions too. How can we increase computational capability? Because part of the challenge in the past has been that it's expensive and complex and time-consuming to bring all the wonderful data to your own computer. So cloud-based data processing, the ability to have, even when you have intermittent internet, be able to have things processing in the background in the cloud, and then be able to have hopefully shareable code that can be repeated in different regions around the world. We see exciting sort of software advances and network advances making this possible.
Great. Jeff, the question for you is, and it's a long-standing one, power on the surface of Mars. Is solar power going to be sufficient to make enough fuel to get us home? So talk to us about that.
I had a graduate student finish last year, and his thesis was looking at a detailed modeling of a human-scale version of MOXIE to produce the amount of oxygen you need. Roughly 25 kilowatts. And yeah, you can. I mean, the space station has over 100 kilowatt, you know,
Earth is a lot closer to the...
well, the Earth is closer, but the problem on Mars is, first of all, there's day and night. And if you're going to run an oxygen production facility, you don't want to shut it down every day. That's one of the problems we have in MOXIE. Most of our power goes in heating it up every time we want to make a run every other month. So you'd need a big battery storage system or fuel cells, more mass. Also, you have dust accumulating. You know, how are you going to clean the solar panels? I think, you know, whether it's nuclear fission is all that we have available now, although if some of the work that's come out of MIT pans out, we may have nuclear fusion 10 years from now, which would be great. But you want to do human exploration, you need a lot of power. And once you get to planetary surfaces, solar power just isn't going to hack it on Mars.
Great, yeah. Okay, so we're running short on time, and I want to get a couple more questions in. So first, one for you two. There are a variety of questions about how these small satellites can help us make observations to address climate change, both mitigation, adaptation. So if the two of you could take a quick whack at those.
Yeah, so small satellites are great because, again, you have more of them, you can get more frequent updates. You can also put more different types of cameras on them. You can put hyperspectral sensors on them, which can sense changes in chemical composition. You do have to calibrate them very well, and you do have to have AI algorithms that can train on hundreds of very narrow channels of data and be able to use them. So these things are valuable. You have weather sensors of several different varieties. People are starting to use small satellites now for even things like synthetic aperture radar, small radar systems, altimetry systems, and things like that that can provide additional information about activities below. There are very successful companies that do radio frequency signal monitoring to kind of track where things are happening. Ships are, for example, or where ships are that should not be there. And so there's a lot of those types of technologies. They all have a role for climate change. And as we're figuring out the most impactful forcing factors, carbon dioxide, methane, similar things like that, we can look for sources and then take diplomatic action, where I'll hand it over to Danielle. I mean, you have this data, but somebody needs to be able to do something with it. And I think that's where I kind of pass over to you here.
What a great summary. And I'll just emphasize in particular, we're in a nice period of innovation in methane in particular. Greenhouse gases include multiple, including water, but CO2 and methane are so important. And right now, several organizations, nonprofit and for-profit, are really trying to increase the ability to estimate methane emissions from space. And what we really need is this combination of what you might call the traditional government satellite, usually larger and longer lasting, but sees more regional view, with some of these innovative experimental satellites coming from non-government sources. So a few things to watch out for as you see new methane satellites. Our team is involved in a project trying to help the government of Brazil, in this case in the city of Rio de Janeiro. They have traditional techniques for making little surveys of where they think methane emissions are happening. We want to compare that with the space-based data. So that's where the policy can come right into play at the local scale often. And so we are hoping to demonstrate or to understand how well these novel methane emissions will be able to be tracked from space and compared to local action to hopefully help reduce that.
Great. Okay, and Jeff, the last question's for you. When are we going to send humans to Mars?
People always ask me that, and
So we're asking you that.
Yeah, and I never answer because I don't know. It's going to depend on so many things. I mentioned in my talk a few of the things that we're going to have to look for, but I think absolutely we're going to have a successful return to the moon program. You know, it's been 50 years since we've operated on the surface of another planetary body. And the people who did it in Apollo aren't around anymore, so we got to learn how to do it again. And I think if we have a successful moon program, a lot of the technologies that we're going to need for going to Mars will be tested on the moon. And so after we've gotten back to the moon and we've operated then for a few years, maybe I'll be ready to answer your question. How about that?
Yeah, that sounds great. Okay, let's thank our panelists. Thank you. Okay, we're going to take a break and then back for some alumni awards. So.
Please welcome to the stage MIT Alumni Association President Steve Baker.
Good morning, everyone. Welcome back to our Tech Day program. Thank you all. I'm Steve Baker, and I'm honored to be entering my final month as MIT Alumni Association President. What a way to cap a great year. Tech Day is one of the Institute's most enduring traditions, and a celebration of the desire of our MIT community to never stop learning and never stop problem solving. We all share that as alumni. Another tenet of our community, as you know, is the application of our knowledge in service to society. During the past few years, the MIT Alumni Association has introduced several outstanding new initiatives, and the creation of the MIT Alumni Better Service Award is among the most significant. Now in its second year, this award honors alumni who have proven an ability, passion, and unwavering commitment to the MIT ideal of working wisely, creatively, and effectively for the betterment of humankind. The Service Award was created in complement with the MIT Alumni Association's long-standing leadership awards. While those recognize service to the MIT community, this new honor celebrates the service that our alumni provide to their communities around the world. And when the Alumni Association puts out the call for nominations for the Service Award, we are amazed to receive so many worthy submissions for consideration. This year, the awards committee for the Alumni Association Board of Directors decided to honor not one, not two, but 3 Better World Service Award recipients. And I'm proud to share with you why all 3 have been risen to the top of the nominations. Please join me in congratulating Vanessa Filiberti Bautista from the class of 1991, Oluwasegun Ige, who holds an SM and PhD from MIT, and Donald Ray, who also holds a PhD. Donald is watching, yep, I'm sorry. Donald is watching with us online. Vanessa and Segun, would you please join me on stage? Congratulations. Congratulations. Please stand over here while I read your citation. Vanessa is an outstanding leader who has committed herself to the cause of enabling equal access for technological jobs for underrepresented populations. Her work in creating, leading, and supporting programs for education, job training, and career development has enabled hundreds of racial and ethnic minorities and economically disadvantaged individuals to find life-changing opportunities to achieve their career and life goals. She has inspired countless young technologists to find their place and their worth in their work. As a lead for the women's community within the workplace, Vanessa has organized early in career activities, mentorship rings, and even argued with architects to include nursing facilities that new mothers need when they return to work. Vanessa has focused her service-related efforts on equity and inclusion, creating opportunities and working tirelessly to promote diversity, equity, and inclusion. Please join me in congratulating Vanessa. Vanessa. Congratulations. Actually, let's step forward a moment. Let's get a photo. Just congratulations very much. Well done. Well deserved. We also have an award for you. We'll present after. and now Sagan. Sagan has performed sustained, innovative, and impactful community service in Africa for more than 14 years. His desire to expand African educational opportunities led him to found the Anike Foundation in 2007 with one clear purpose: making education accessible to improve the livelihoods of individuals in Africa. Anika is a small nonprofit that uses its limited resources through its partnership. It now has a network of over 200 partners in 20 countries across the continent, touching thousands of lives through its funding of essential programs. The foundation is 100% volunteer-based, and he has grown his diverse team of volunteers to over 70 individuals in 12 countries around the world. Sagan's effort to bridge the education gap in Africa, the education gap between Africa and the developed world, is exemplary. Please join me in congratulating Sagan. Congratulations. Thank you. Congratulations. Well deserved. Thank you very much. Finally, watching on the live stream, Donald Ray. Donald's vision was to pair retired or semi-retired STEM professionals with K-12 educators to enable those educators to have a rich resource for their classroom studies across STEM topics. To that end, he founded the American Association for Advancement of Science STEM Volunteers Program in concert with the AAAS leadership in 2004. Serving just one single school district in that first year, the program has grown to encompass 5 school districts in the greater DC metro area and includes more than 180 volunteers serving more than 6,000 students. Through the foundation, Donald has made a deep impact on the community with his excellent training and delegation skills and his dedicated spirit. Please join me in congratulating him. I'm going to wave at him at home, and let's give him a round of applause, too. Vanessa, Sagan, and Donald, on behalf of the MIT alumni community in the audience today and those watching around the world, we feel a profound sense of pride knowing that you are part of the MIT alumni community. And we thank you for your service in helping to create a better world. Thank you. And now back to our Tech Day program.
Please welcome to the stage MIT professor Taylor Perron.
Good morning, everyone. I want to start with no pictures and a question for you. Do you ever wonder what your life would be like if a few key details were different? What if you'd chosen a different career? What if you were born a generation earlier? What if you'd never come to MIT? Now, I know you would have turned out fine, but we wouldn't be here together today. We'll never know the answers to any of these questions. We only get one reality. And that is what I think is so cool about Earth and planets. They actually give you glimpses of alternate realities. Let me give you a few examples to illustrate what I mean. So I'm an Earth scientist, and sometimes I wonder, what would Earth be like? What would landscapes be like if there was no life on land? Sounds kind of like dystopian science fiction, right? But as some of you may know, that was actually the case for the first 90% of Earth's history. And now geologists can use ancient rocks to try to reconstruct what landscapes were like before there were plants or animals on the continents. Some of my MIT colleagues discover planets that are orbiting other stars. Every single one of those planetary systems is an alternate reality, and some of them are wildly different from our own. And how about this one? What would landscapes on Earth be like if gravity was 7 times weaker, and if you replaced all the water in the hydrologic cycle with liquid natural gas. Now, the MIT lab safety people are watching this and thinking, what is he going to try to do? But they don't have to worry. I'm not going to do that experiment because the solar system has already done it for us. This is Saturn's moon Titan, my alternate reality of choice. It looks like a big orange ball because it's the only moon in the solar system that has a thick atmosphere. And that atmosphere contains organic compounds like methane that block light. You know how it's hard to see the horizon in a city with smog? Well, Titan has smog that would make 1970s Los Angeles proud. And so for a long time, we had no idea what the surface looked like. We knew that it was cold, minus 290 degrees Fahrenheit. We knew that it's made of ice instead of rock. But beyond that, there were few details. So at this point, you're thinking, wait a minute. His title was Earth's twin. That doesn't sound like Earth's twin. Let me show you what we saw when we finally got a glimpse of Titan's surface. The reason we finally got a glimpse of Titan's surface was the Cassini-Huygens spacecraft mission, which went into orbit around Saturn in 2004. And as it was flying past Titan in early 2005, it dropped the Huygens probe, which is the little gold dome you see on the left-hand side of the spacecraft, down through Titan's atmosphere. Here's an animation that was pieced together from pictures that were taken by the Huygens probe as it was parachuting down to Titan's surface. And you can see that the first thing we saw when we finally got a close-up look at Titan's surface was networks of river valleys carved into hills made of ice. Turns out Titan has weather a lot like Earth's, but the clouds, the raindrops, the liquid flowing through the rivers is methane, liquid natural gas, instead of water. Titan has mountains, but the mountains are made of ice and organic compounds instead of rock. Titan also has lakes, and its biggest lakes are as big as Earth's biggest lakes, but they're filled with liquid methane and ethane instead of water. So this is what I mean with my title. In terms of weather and in terms of landscapes, Titan is Earth's twin. And this is more exciting and more useful than any experiment that I could do in a lab. So what have we learned by studying this experiment that the solar system has given us? One of the most obvious lessons, which is especially interesting for us here on Earth, is that clearly there's more than one way to make a stable climate. There's more than one way to make a hydrologic cycle, even if there's no hydro in it. In my group, we've been piecing together the details of the climate and environment of Titan's surface to try to understand what that stable climate is like. We study the mechanics of landscapes. We study rivers, coasts, mountains. We use a variety of techniques, including laboratory experiments. We go out in the field to some pretty ugly places. And we use numerical simulations. And one of our specialties is in taking the knowledge that we gain about landscapes here on Earth and translating them to planetary environments and accounting for the differences in gravity, atmosphere, materials, so we can learn something about the environments of other worlds. One of the challenges in our Titan research is that we can't always see these landscapes up close. And so sometimes we have to get creative and invent techniques that we would never bother to use on Earth, where we can actually go and stand on the landscape and do field work. As an example, we've developed a technique that allows us to measure the rate of flow through rivers on Titan or other worlds just with measurements of the width of the channel and how steep the river is. And both of those are things that we can actually observe remotely. Now, we have to test these ideas on Earth to make sure we get the right answer in a place where we know what that answer is before we apply them to other worlds. And once we do that, we've learned that Titan's largest rivers might have flow rates as large as the Mississippi River on Earth, even though Titan is a smaller world. And this is also useful because it allows us to estimate the rate of rainfall that's feeding those rivers. And so we've estimated that rainfall rates on Titan may be comparable to what you get during storms in dry regions on Earth. We've also studied coasts. And one of the frustrating things about Titan's coasts is that we can't see them up close. We can't even tell if there are waves on the surface of the lakes, or if it's mirror smooth, like the Charles Basin on a really calm day. So we've developed a technique that lets us take the shape of a coastline and reconstruct whether there's been wave erosion taking place, and even whether there's a dominant wind direction. And we see evidence that some of Titan's coasts are consistent with the presence of waves. One thing I want to point out, too, is that studying planetary landscapes also has some benefits for us back here on Earth. If you're in the business of building theories to try to predict what's going to happen to landforms on other planets, and you have to be able to apply those theories regardless of differences in gravity or atmospheres or materials, you have to make them really robust and flexible. And if you can do that, it makes it more likely that those theories and models will hold up under the full range of conditions that we see here on Earth, even if those conditions involve natural hazards, even if those conditions involve engineered landscapes. So studying planetary landscapes helps us build better theories for Earth. Some of the results we've obtained for Titan are still predictions, and they'll have to wait for future spacecraft missions to be able to test them. So if any of this has piqued your interest, stay tuned, because the Dragonfly mission to Titan, which by the way is led by an MIT alum, is scheduled to land on Titan's surface in 2034 and continue to explore there. And given how much we learned when the Huygens probe touched down on the surface of Titan almost 20 years ago, Dragonfly is guaranteed to surprise us. So stay tuned, thank you, and I'll see you in 2034.
Please welcome to the stage MIT Assistant Professor Erin Kara.
Good morning. All right, I'd like you to take a listen with me. The sound that you just heard is what a black hole sounds like. And I'll tell you, the first time that I heard that sound, I got shivers down my spine. And it's not because it's kind of spooky sounding, which it is, but it's because I could hear the general relativity in that sound. So what I want to tell you about today is, how we use these echoes to understand black holes and how they grow. And I hope by the end of this talk, you too will be able to hear the general relativity. Okay, so let's start with this beautiful image taken with the James Webb Space Telescope, our newest, biggest toy in astronomy. And when this image first came out, a lot of people were looking at that beautiful spiral galaxy that you see in the foreground. But what I was looking at, and what a lot of astronomers are looking at, are not the foreground galaxies, but the background galaxies. Look at all of those galaxies, those smudges there in the background. All of those are galaxies. Some of them are in the nearby universe. That means something like 100 million light years away. And some of them are from the very beginnings of the universe, when the universe was, a few 100 million years old. And what really gets me is that at the center of each one of those galaxies is a supermassive black hole at the center. That's 1 million or 1 billion times the mass of the sun. And one of the things that we astronomers want to understand is, how did they get so big in the first place? How do you form a black hole and have it grow so big to become 1 million or 1 billion times the mass of the sun? One of the ways that they do grow, that we know of, is that material falls into them. Gas, dust, stars are falling into black holes, and they grow from that accretion of matter. And we know that they're growing because we have observations like this. This is 3C273, a galaxy and a black hole in that galaxy that's 1 million times further away from that star that you see in the bottom right-hand panel. But what's amazing is that this black hole is even brighter than the star that's 1 million times closer. And so maybe you remember from 802, electricity and magnetism, that the luminosity goes as the distance squared. And so what that means is that 3C273 is actually 1 trillion times more luminous than that foreground star. And the only thing in the universe that can create that amazing amount of luminosity is the accretion of gas onto a black hole. Gas it funnels towards the black hole, it loses its gravitational potential energy, and that energy is released in the form of radiation. So much radiation that it totally outshines all of the stars in the galaxy. And what we want to understand is, how does this process work in detail? How do you go from matter falling in to this incredible amount of radiation coming out? And to answer that question, we really need to zoom in to the innermost regions around black holes, to the event horizon scales, where most of the energy is being released. And so, what's awesome is now when I say we need to zoom in to event horizon scales around black holes, you all have an image of what that looks like. This image, taken by the Event Horizon Telescope, is an amazing feat of engineering. And what we've done here, what this Event Horizon Telescope collaboration has done, is to directly image the very close environments, the event horizon scales around this black hole M87. That's about 1 billion times the mass of the sun. So what's key, though, is that the Event Horizon Telescope can only work on black holes that are not actively growing, on black holes where the amount of matter that's falling into it is not very much. It only works because the density of that gas is low. But how about those black holes like 3C273 that were so bright, that were actively growing? What do they look like? Well, that's what they look like. Any telescope out there, no current telescope, no future telescope, is going to be able to directly image the event horizon scales around a black hole. And so that's why we need to get a little bit more creative and use echoes of light to reconstruct what we think it looks like around a black hole. And so that's what I want to tell you, that's what my research is about and what I want to tell you about today. So, when my friends and family ask me, like, Erin, what is it that you actually do all day? And I try to explain these light echoes, I find myself often, using the analogy of sound, right? Sound echoes are something that we all can appreciate, Here's a little demonstration. I will clap my hands. You hear the sound of my clapping directly, that flash of sound, but you also hear the echoes off of the walls, right? And if you could map out all of those echoes in time, you take that time delay, those echoes, you multiply it by the speed of sound, and then you can perfectly map out this room that we're in without directly imaging it with your eyes. So this is what we're trying to do with black holes and what we do with these accreting, growing black holes. So the schematic that you're seeing here is, we'll go back and play it again, is a schematic that the NASA press office put together for me. So what you see here is a black hole on the bottom right-hand corner. And gas, this orange bit on the bottom, is gas that's funneling into the black hole. And you're seeing like a cross-section of that gas that's funneling in. And what we see in these systems are that they are very abundant in X-ray emission. X-rays are coming from this hot plasma around the black hole that we call the X-ray corona, because it's around the black hole. And the blue there is that shining source of X-ray light. In the sound analogy, it's that clap. We see a flash of light from the X-ray corona, but we also see that corona shines back down onto that inflowing gas, that accretion disk, and that disk then echoes the light. And since we can measure those echoes, that light that is being reprocessed off of that accretion disk, and because we know that light travels at the speed of light, then we can use that to reconstruct what that looks like around that black hole, how gas funnels into the black hole. So it's not totally as simple as what I've described to you just now. It's not quite so simple. One of the things that we have to account for is the fact that we are around a black hole, that the space-time around that black hole is very curved. And so the light that is echoing off of this accretion disk, this inflowing gas, is distorted from the strong gravitational effects around the black hole. So for instance, if we had a ray of light, this blue wavelength here, traveling through space, we would see it as a blue light ray. But since that light is coming from around a black hole and is traveling through the very curved space-time of black hole, as that light escapes from the strong potential well of the black hole, its wavelength gets stretched. This is what we call the gravitational redshift, because the wavelength of the light gets stretched to redder wavelengths as it climbs out of the potential well of the black hole. And that's one of the things that we have to account for when we want to reconstruct these echoes into an image of the black hole. So that takes me to getting back to the sound that you just heard. During the pandemic, we were all alone, and I was, in my apartment, I was like, I need to communicate, I need to reach out with some people. And I thought, this project is kind of a fun side project that I always wanted to do. Let's take our light echo simulations, our general relativistic light ray tracing simulations, and convert them into sound and see what that sounds like. And what you can see here on the top, whoops, not yet. On the top here is that echo of sound that I told you about originally. On the bottom is a simulation of the light echoes from around the black hole. And it's actually kind of amazing that they even look anything like each other, right? We have this primary flash of radiation from the corona, and then it echoes out and reprocesses off of the accretion disk over time. So what we did with colleagues at MIT in the music and anthropology department, that's one of the things I love about MIT, is that even the musicians and the anthropologists are tech nerds, and they love black holes. We converted these light echoes into sound. So we took the pitch of the frequency of the photon, the wavelength of the photon, and we translated that into the pitch of the sound that you're going to hear. So let's play that sound again. This is an image of the black hole. The circle there is the event horizon, and you're going to hear now the reprocessing, the echo off of that irradiated accretion disk. And I want you to listen for the doo. That's the gravitational redshift. That's those photons that are escaping close to the potential well of the black hole that are being stretched to longer wavelengths. Did you hear the general relativity? You got it? Okay, that's all I have for you today. I just want to thank my research group and MIT School of Science. Thank you.
Please welcome to the stage MIT Vice President for Research, Maria Zuber.
Okay, thanks everybody. We're back, and we're going to get started right away with the second panel. So I'm going to call Taylor and Erin to come out and start the questioning. So get your questions in. If you're streaming in, there's a Slido box beneath the stream, And if you're here in the audience, you can scan the QR code and give us the same kind of interesting questions that you gave us in the last session. Okay, so I have to start with Erin. I resist, okay? On my cell phone, my ringtone for text messages is the 2015 LIGO black hole collision, you know? And I'm going to try to play it for you, okay? So, don't we live in an amazing world where, now don't start texting me, okay? Or else we're going to be in trouble here. So I would always say, in terms of why we explore space, you go out, you look at things you've never seen before, and then you go back, okay? And you look with a different set of eyes, okay? And now you can look with a different set of ears, okay? And we're really getting into the age of not only the optical and, you know, far-reaching wavelengths and very short wavelengths, but also acoustics. And so could you reflect upon that in terms of, you know, not just your own X-ray area, but the broader area of black holes, and just what looking with all these different kind of sensors has meant for progress here?
Yeah, that's a great question. I think it is like an amazing time to be a black hole astrophysicist right now. Not only are we seeing, you know, electromagnetic light, but we're also seeing the bending of space-time from black holes that are merging together. And you know, as we go out and we find more of these, you know, bending of space-time, and we have just telescopes that are not just pointing at one single black hole that we know about, but just like looking for kind of just exotic objects that are just going flash in the sky. Like, we are constantly learning and being surprised, and it's just the universe is blowing our mind like every day. And I think it's kind of an exciting time because we have all of these telescopes that are coming online at the same time that are just finding things that we never thought possible that the universe can do. And the biggest thing going forward, I think, is what we call multi-messenger astronomy, is not just measuring the light, but simultaneously measuring your cell phone ding, the gravitational waves, the rippling of space-time. LIGO, which was largely built here at MIT, and Ray Weiss received the Nobel Prize for his developments building this gravitational wave network. They're just starting up operations again, and we're all like just waiting for the next big thing. It's exciting.
Great, thank you. So Taylor, I didn't want you to feel acoustically disadvantaged here, okay? And so we had the audio team put together a sound from this solar system, and we're going to play that now. But everybody, be quiet because it's low frequency. Any idea what that is?
A quiz. Was it derived from Huygens?
No.
I don't know.
Wrong planet. That is an actual audio of the Ingenuity helicopter flying on Mars. So it turns out on the Perseverance rover, there are 2 microphones, and we heard the first 2 actual measured sounds, not converted sounds, of one spacecraft listening to another spacecraft on another planet.
Thank you for including me.
But I have another question too. So the Titan analogy is really interesting, and actually, Titan is the only other planetary body in our solar system that has a nitrogen atmosphere like Earth. Okay, far more common atmospheres are carbon dioxide, and of course, we're worried a lot about the accumulation of carbon dioxide in the atmosphere of our planet. And in your talk, you just really nicely laid out the idea of nature doing another experiment for us in some other part of the solar system. So 2 other planets that have carbon dioxide atmospheres are one, Mars, okay, which lost most of its atmosphere, and then Venus, which has had a runaway greenhouse. So maybe reflect upon if there's anything to be learned about what's happening on our own Earth with the accumulation of CO2 from these 2 other natural experiments that we have bookending the Earth in our journey around the sun.
Yeah, that's a great question. And that is probably one of the first big atmospheric natural experiments in the solar system that we became acutely aware of, is that the trajectories of Mars and Venus, even though there are a lot of similarities to Earth, have been so different and have turned out so differently now. Obviously, Mars now very cold, Venus rather uncomfortably hot and high pressure. And so one of the things I mentioned when I was speaking to you earlier is that it's interesting that we see that Titan, at least right now, has a stable climate. And Venus and Mars, in terms of their CO2 greenhouse, have taught us that that's not a given, right? Things can kind of go in a different direction. So this is a major goal of those of us who pay attention to terrestrial planets, rocky planets, to try to understand their climates. And one of the things that we've been trying to do, at least on Mars and the Mars community in general, is to understand what the early climate was like, using some clues on the surface to maybe tell us what was happening through time in terms of that atmospheric evolution. How long did the CO2 greenhouse effect on Mars stick around and maybe keep the surface, if not as warm as on Earth, maybe warmer than it is now? And then on Venus, what happened to put all of that CO2 in the atmosphere with no way of being recycled, kind of like it is on Earth? And so the geologists get in on this too, because we try to understand what regulates the concentration of CO2 in our atmosphere. Plate tectonics probably plays a big role in that. And so we'd like to understand what about Mars and Venus prevented a regulatory system like that.
Great, thank you. All right, we're going to now move to our questions from our alumni friends. Erin, let's start with you. There's a question asking you to describe the shape, the 3-dimensional shape of the accretion disk. Does it look like a bagel? Is it stable? Is it unstable? Clue us in here.
Yeah, so you'll remember now from 801, right? Conservation of angular momentum. Sometimes I get asked, like, why isn't everything just sucked into the black hole, right? And it's because of conservation of angular momentum, right? Imagine you have a black hole here and you're trying to throw a particle of gas into that black hole. You know, you'd have to have impossibly precise aim to hit it directly. And more likely what's going to happen is that that particle of gas is going to get whipped around the black hole, right? And it's not just one particle of gas, it's many particles of gas that are interacting with each other and the black hole. And because because of conservation of angular momentum, they start forming into a disk around the black hole, orbiting around the black hole in a disk. And then it turns, so, you know, it's kind of like a donut or like a flat disk. But what we see is actually something a lot more complex. And that's because of the bending of light around in the strong potential well of the black hole. So what's crazy about relativity is that, you know, light takes straight paths, but it's that space is curved, so, you know, this accretion disk, this flat accretion disk, that, you know, to you, if you're looking at it edge on, maybe you wouldn't see the back side of that disk. But because some of those photons from the accretion disk, they get bent over the black hole, and we see them into our line of sight. And so part of that image from the Event Horizon Telescope that you saw is light from the backside of the black hole that's being bent into our line of sight. And so it looks, that flat disk then starts to appear kind of more bulbous shaped because of those relativistic effects.
Great, thank you. Taylor, there's a question here about how does Titan retain its atmosphere? Is there solar wind stripping did a number on Mars? What's going on out in the Saturnian system?
Yeah. So Titan's atmosphere, in fact, is more massive than Earth's. The only moon out of hundreds that seems to have managed to do that. And there are a bunch of mysteries about it, one of which is, well, why does it have all this methane? It breaks down in the atmosphere due to the sunlight, so there probably is a source replenishing it. But one possible answer to that question is that Titan spends enough time in the close embrace of Saturn and Saturn's magnetosphere that it might shield it from the stripping of its atmosphere. So between that and a source of gases, that apparently has helped it hang on to its atmosphere.
Okay. Erin, back to you. What do you assume about the mass distribution inside the black hole, and why? Oh.
So we have no information from within the event horizon of the black hole. And so we assume that it's just, once the matter goes into the black hole, it's just a point mass that grows larger and larger. Sometimes I think that that's a little bit disappointing to people from the perspective of an observational astrophysicist, is what happens, what's the mass distribution. I mean, as far as I kind of see, is that matter just flows through that accretion disk. Eventually it'll go past the event horizon and it just grows the black hole. And it has no distribution in space because it ends up in the singularity. And so what we can measure, even though we have no information from outside of the event horizon, we can see things, we can infer properties of the black hole, its mass, how fast it's rotating, because all of that has an effect on the space-time geometry around the event horizon. So the more massive your black hole, the larger your event horizon is going to be. And so if you can measure, the size of your accretion disk will also scale with the mass of the black hole. Stars orbiting around the inner regions around the black hole will travel at a particular velocity because of that particular mass of the black hole. And then we can infer also things like the spin of the black hole, which is one of the topics that I'm really excited about. That's a little bit harder to measure than the mass of the black hole, but again, it changes the geometry, the space-time geometry that we can even observe outside of the event horizon. So we can infer those properties of the black hole itself, even from outside of the event horizon. Yeah.
Cool. All right, back to Taylor. When Dragonfly gets information from Titan in, this says 2023, but it should be 2034, how long will it take before the information is received and analyzed and the results reported? So people are eager.
They are
obviously.
eager. Well, I'm glad to hear that. The bad news is it takes a long time to get to Saturn. So the launch is scheduled for 2027, so it takes about 7 years to get there. It is still an if, because we haven't launched yet, but hopefully when the data come back. One thing we've learned from Cassini-Huygens, which was a very long-lived mission, which was in orbit around Saturn from 2004 to 2017, is that it can sustain decades of research because almost everything we're learning is new. And this time, Dragonfly is planned to be able to move around the surface because it's an octocopter that can visit multiple locations. So I would expect that after the landing happens that new results will start to come in within months, but I'm sure we'll learn for a long time after that.
Is it going to carry a microphone?
It has a seismometer, so it's actually going to be able to do some
Excellent. Oh, yeah,
geophysics.
good. That'll work, yeah. Okay, Erin. When I was a student, we used the equation you referenced to use the luminosity to calculate distance to stars. How did you know the image you showed was a black hole that was both brighter and farther away?
Yeah, this is like one of those amazing discoveries that, so this was back in 1963. Astronomers were starting to see these objects that they called quasi-stellar objects. And they called them that because they didn't know what they were, but they looked sort of like stars. And so that's why they were called quasi-stellar objects. And the major breakthrough came because they realized that, no, it's not a star. It's a million times further away than that. And the way that they discovered that, Martin Schmidt saw emission lines in the spectrum. So, transitions between photons being produced from hydrogen atoms and helium atoms, and they produce emission lines at particular wavelengths. And we know very well what those wavelengths are. And when they made a spectrum, they saw like these emission lines, but they didn't. What they finally were able to do was realize, okay, they've all been shifted because the universe is expanding and the universe is moving away from us. And if light has traveled from 1 million light years away, it's traveling through this space that is expanding and accelerating away from us. And so as those photons travel to us, similar to the gravitational redshift effect, as those photons travel through this universe that's expanding, they will get shifted to longer and longer wavelengths. And because all of those emission lines were shifted by the same amount, then they could infer that light must have been coming from very far away. And that really just broke open the entire field. And yeah, it was a major breakthrough, but yeah.
Great. These are pretty technical questions.
Yeah,
so
good ones.
people are not taking the weekend off here intellectually. So.
These are MIT alums.
Yeah.
All right, and along those lines, Taylor, in your landform modeling, how do you account for the differences resulting from methane versus water and planetary gravity? Clearly, that must impact how the surfaces develop.
Absolutely. And this is one of the tricky things about taking results from Earth and trying to apply them to other planets, is that if you build your theory by fitting to a bunch of data for a particular place on Earth, and you don't explicitly account for things like gravity, the density and viscosity of the liquids, good luck when you try to apply that on Titan. So you really have to make sure that you include explicit dependence on gravity, material properties. There are a few things we can do. We can account for the relative buoyancy of the sediment moving through a river, for example. So we know how to do that on Earth, where it's rock and water. By analogy, we can figure out how to do that on Titan when it's either ice or organics in liquid methane or liquid ethane. And then in other cases, we can actually take the differences in gravity that are contained in the theories we develop and apply them as long as as that appears in the equations. Another friend of ours is turbulence. One thing that people always ask is, what if you have a difference in the viscosity of the liquids? And it turns out that liquid methane is less viscous, it's more runny than liquid water on Earth. But it turns out that once things become fully turbulent, where you have lots of fluctuations in the speed of the flow, that some of these characteristics, like resistance to flow in rivers, become roughly constant. So you can actually, in some cases, neglect the difference in viscosity as long as you're sure you have the right flow conditions.
Oh.
Technical question, technical answer, I guess.
Yeah.
Right? Yeah.
Okay, and we're just about out of time, but we have the perfect closing question for you here, Erin, okay? How does black hole research allow researchers to learn more about space itself? What information arises from the study of black holes?
Whoa, that's a big question to answer in 19 seconds. I think that what is amazing about black holes, right, and the reason that I study black holes is that they are vitally important for understanding why the galaxy looks the way that it does. And that's actually like a major puzzle. You know, these black holes sit in the centers of galaxies that are 1,000 times more massive. So why should the galaxy care at all what that puny little black hole is doing? But it turns out that the black hole actually dictates how the galaxy evolves. And it's because that accretion of gas is releasing all of this energy that can affect the galaxy on large scales. And so if we can understand how the growth of black holes leads to the production of this radiation, we can understand how galaxies evolve, why our Milky Way looks the way that it does. And I think that that's like ultimately the big question is, you know, why are we here? Why does the solar system look the way that it does? And black holes are actually a very important piece of that puzzle.
Great. Well, let's thank our panelists. Erin and Taylor, great job. Okay, we're having fun now. Well, the Alumni Society leadership promised you a surprise, and the time has come to deliver. We've got two alums who really wanted to be with us today, but they just couldn't get the right connecting flights to work. No. So they're about 250 miles away, and I know that doesn't sound like too much, but thinking about the topic of today's event, you're probably catching on by now that we're talking about 250 miles that way. Okay? And so a couple of weeks ago, I was out in Pasadena at the Jet Propulsion Laboratory helping out a little bit with the next Mars mission. And I had the distinct pleasure of interviewing Steve Bowen and Woody Hoberg, MIT alums who are currently on the International Space Station. So we're going to play now a video of that conversation. And Whitney and her team just had an awful lot of fun planning this presentation for you, and I hope you all enjoy it as much as the team enjoyed putting it together and bringing it to you. So stay tuned.
Station Houston, are you ready for the event?
Station, this is Professor Zuber. How do you hear me?
And Professor Zuber, we hear you loud and clear. How do you hear us?
I hear you just great. So it's a real pleasure to see you again, Woody. Last time we met in person was on the MIT campus, and Steve, a pleasure to meet you for the first time. So for you both, I'm the Vice President for Research at MIT and also a professor in the EAPS department, and it's just fantastic to speak with you both today. Okay, well, I'm actually broadcasting here from out on the West Coast with our partners at the Jet Propulsion Lab. So I know you both wanted to beam into our alumni reunion, especially because Tech Day this year is called Research from Above and Beyond MIT in Space. And I'm the moderator for this year's event, and I thought we needed to include those who are physically closest to the work. And so you two were naturals to think about.
Well, thank you, Professor Zuber. We certainly wish we could be there to experience the excitement in person, but it's just thinking about MIT, it's such a special place, really one of the most amazing places on Earth.
So Woody, you were the faculty advisor for the Rocket Club when you were a professor back at MIT. I'm sure we have some Rocket Club alums who are tuning in today. Do you want to give them a shout out?
Yes, absolutely. Hello, MIT Rocket Team. Rocketry was actually a big part of my early development. That's why, as a young faculty member at MIT, it was an honor and a privilege to get to be their faculty mentor. And I'm just so proud of all the students that not only work on really hard classes at MIT, but also enjoy getting their hands dirty playing with some real hardware. I know I learned a lot from doing that. And it's awesome to see students that are also excited about that. I will also give 2 quick shout outs to the MIT Outing Club and the MIT Ski Team. Both of those organizations taught me a lot about teamwork and appreciating the outdoors, and they certainly left a mark on me as an undergraduate.
So for both of you, what was the biggest surprise about going into space? You know, obviously you train and you train and you train and you prepare, and then you get up there and it's amazing, right?
Yes, there is that. The thing that I have to say this every single time, that the thing that amazes me is how much doesn't surprise us when we get here, because the training is so good and so intense, and then the opportunity to be able to work with people who have been here before really prepares you well for when you get here, what you're going to experience, the pleasant as well as the unpleasant. You know, we kind of discussed it all. And certain things never get old. For instance, floating just never gets old. The view out the window never gets old. I don't know, what do you think, Woody? Still on.
Yeah, for me, I think the single most amazing part has been watching how the human body evolves and adapts to new environments. That is truly remarkable. And it's everything from watching our vestibular system change to the fluid shifts in our body. It's a pretty extreme change in environment. And the human body just, you know, I grew about 3 inches up here, spinal elongation, just from the loading being different. And all sorts of other changes that you definitely feel and notice, but it's just amazing watching the body adapt. And it's also impressive mentally, just how quickly you get used to new environments. I still remember, this is my first flight, unlike Steve, but I remember the feeling of being on the ground and not knowing quite what it would be like to be always weightless and to be in space. It's a new experience. And have this amazing ride up on the rocket, 8 minutes of excitement, flying uphill, and then second engine cutoff, and you're weightless. And that was a little over 60 days ago for me, and I've been weightless ever since. And it's amazing how quickly you get used to that being your new normal.
So Woody, you talked about the influence of rocketry when you were growing up and how it got you interested, how interested you were. Steve, were you always interested in space, or did you develop that interest at a later time?
Oh no, I was always interested in space. I'm significantly older than Woody, shall I say, and so I actually watched Neil Armstrong step onto the moon in 1969, and so as a very young child, it sort of set the bit in my brain. I never thought it was possible, though. I mean, I joined the submarine force after graduating from college. And it didn't seem like a career path option, but I applied and I was accepted, and it's which is like winning the lottery in my mind, and it's been amazing ever since. But it was always back there, but it's one of those things you never think you can do, and so just sort of out there for everybody. You know, the worst they can say is no, and that would have been okay. I would have been perfectly happy, but this is just an amazing opportunity, amazing experience. And I want to add on to something that Woody was saying about how the body adapts. And this is not a fashion statement. This is actually part of the science we do up here. I don't usually wear headbands, but I actually have a whole suit with a suite of tools that are measuring part of my biometrics. And so we are our own experiments as well.
So I know that you both have a message that you'd like to transmit to the surface here.
Welcome aboard, Sally. It's great to hear that you've got a tremendous position and tremendous responsibility for the school. That's incredible.
Welcome to MIT and the amazing position you're taking on. We're really honored to welcome you aboard the International Space Station, and we wish you very well with the mission you are continuing forge ahead with back at MIT. It's near and dear to my heart, and we're so proud of the work you're doing every day.
Okay, well, they're letting me know that we're coming to the end of our time, so I'd like to take this opportunity to thank both of you, to congratulate you for representing MIT in such a dramatic and hopeful way, and thank you for being a part of MIT's Tech Day. Steve and Woody.
Yeah, thank you. It's such a pleasure to get to talk with you, Professor Zuber, and to the MIT community. The work that you are doing is so important, and whether you're a student learning and getting ready to contribute as a leader in science or technology, we need you. We need you for the challenges ahead. Or to the faculty members and other members of the MIT community, you're pushing the boundaries, and we're so proud of everything you're doing. Such a special place, and it was just an honor to get to talk to you today.
Station, this is Houston ACR. That concludes our event.
Thank you to all the participants from MIT and JPL. For the ISS, we'll resume normal operational audio communications.
Please welcome to the stage MIT Alumni Association CEO, Whitney Espich.
That was pretty awesome. It gives new meaning to having friends in high places, right? Let's give Professor Zuber one more round of applause for just deep thanks for making that possible. And also just the incredible speakers. It seemed like everyone had smiles on their faces and your brains were working hard. Those questions in the second session were really impressive. So a round of applause to you for really just engaging with our faculty. All right, so normally I would say it's a pretty tough act to follow some amazing MIT alumni astronauts. That doesn't happen very often. But I feel confident that you're going to be just as dazzled by the next set of stars who are going to come to the stage. In just a moment, our 128th MIT Alumni Association President, Steve Baker, and MIT's 18th President, Sally Kornbluth, will join us for a fireside chat. Your Tech Reunions app will tell you all you need to know about these special people, including President Kornbluth's academic trajectory that has brought her to us and to this stage today. This marks not only President Kornbluth's first Tech Reunions, but also her first alumni-exclusive appearance, and we're so delighted to have her continuing in the coming year with a global listening tour for her to meet even more of our alumni community. Her travels will continue the conversation in person as she listens and learns about MIT. Stops will include New York, San Francisco, and London for sure, and we have some more cities to announce in the near future. Before President Kornbluth and Steve Baker sit down for their conversation, we thought it might be fun to remind you all of the MIT she's been brought here to lead with all of you. Let's roll the video.
Hello and welcome, President Kornbluth. Welcome to your first Tech Day.
Well, thank you.
One of the things that I've really enjoyed most about my year as president has been watching the many ways that the Alumni Association and MIT keep our alumni connected, excuse me. And certainly this is one good example. So this is a great moment. Sally, as you know, we have here in Kresge Auditorium many alumni who are celebrating reunion years, as well as people live streaming from around the globe. Wherever you are in the world, the Institute is working to offer up opportunities to once again drink from the fire hose, as we all did as students. And so let's keep the learning going now. We're going to dive into some questions for President that have been synthesized from her listening tour for the last few months. Are you ready?
I am ready.
Okay. I think the first question that might be on folks' minds is, 5 months into your role, and with your inauguration and your first commencement in the books, what do you think of the MIT fire hose so far?
Yeah, it is a fire hose. You know, I have to say, around every corner, every day, I'm learning incredible new things. So for, you know, someone who's curious, this is paradise. It really is. You know, just take this morning. I never heard a black hole sing, and I never heard someone casually say when I was out repairing the Hubble Space Telescope, ... I have to say also, you know, I'm glad there's no quiz at the end of it, because the amount of information flowing in is amazing. I actually mentioned to Steve, I actually had a dream last night that was a variant of the, you know, when you take a class and you never show up at the class and you have to take the exam, you know, that anxiety feeling. I had this dream last night that I was walking along the road with Provost Cindy Barnhart, and she said to me, you know, in order to maintain your status as an MIT faculty member, you have to pass 2 MIT classes every year. I was like, what? Nobody told me that. So anyway, it's been fantastic. I'm learning a lot, but as I said, a quiz might be problematic at this point.
Those GRRs are tough. Since your arrival at MIT in January, you've embarked on an extensive listening tour, as we already mentioned, with students, faculty, staff, postdocs. And what are you hearing across the campus? And are there any overlapping themes that are emerging?
Yeah, absolutely. I mean, I think one thing, and this is probably true at many institutions, but I've really felt it palpably here going from group to group, is this desire to reconnect as a community after the pandemic and thinking about what avenues the administration can provide for establishing some of those reconnections. You know, I've heard a lot of people who are really intensely interested in understanding how the MIT education of today tracks with the needs of our future society. You know, how do we think about our GIRs? How do we think about our majors? How do we think about educational experiences for students outside the classroom? And, you know, there's intense interest in really thinking about pedagogical innovation and how we continue to educate our students in the best way possible. And of course, there's a very strong interest in what MIT is going to do in the arena of climate change. And I spoke to that at my inauguration. And there are, you know, at least 20 to 30% of the Institute, their own research work has, you know, bears on that question. And so really thinking about how MIT has a huge impact on the climate change problem is really on the tip of everyone's tongues in our conversations.
So let's jump to that and go into that a little bit more. You're beginning your time at MIT at a consequential moment for the world. At your inauguration, you called out climate change as a challenge that requires leadership, not just contributions for MIT. Can you share more of your thoughts about that?
Yeah, you know, I think this is also part of what I've heard across all the listening tours is this sort of, you know, MIT is really a place where 1,000 flowers bloom. So when I say there are 20 to 30% of the faculty working on climate change, it's a little bit anybody's guess how many people are working on it, because, you know, in every corner, everyone is so entrepreneurial and so innovative. But part of the issue, I think, for climate change, and also for some of the other big institutional, societal challenges, rather, at this point, is how we make the whole be greater than the sum of the parts.
and how we organize. So I think, I'm starting to think about ways in which we can harness the expertise without dampening the innovation and dampening the entrepreneurial spirit to answer really big questions. And so it's going to require leadership at all levels, at the faculty level. It's going to require some sort of organizational principles in constructing a roadmap that really says, for instance, how do we decarbonize construction, or how do we decarbonize transportation, or whatever the big questions we choose are, how do we harness the collective strength to really directly approach some of these really big questions? And we recently had a conversation with 40 climate change leaders on campus. There's another conversation coming up next week, and we're really just starting to generate ideas and discuss how we might organize around those principles. And I think we can come up with a way to continue the individual innovation and to also state collective goals that will get us to impact on climate change more rapidly.
Well, I know that that's a subject that a lot of people on campus and among the alumni body are very interested in, and they're going to be, I think, a lot of people supporting you in that. So, your listening tour has mostly been on campus, but I know that you have met with alumni during inauguration festival. You said certain other volunteer events, including you met with the Alumni Association Board of Directors this week. Thank you for coming to us.
Yes, that was fun.
How do you plan to expand your understanding of MIT's alumni perspectives?
I mean, I think, first of all, as you know, there are sort of trips planned. Whitney and also Julie Lucas have, plans for me to travel around the country and internationally to meet people. But also, I think alumni are so involved in many aspects of the conversations already going on campus. For example, I know there are alumni organized around climate and sustainability, and so I would invite alumni to contact me to continue some of the conversations that are already underway. I think there are many ways that alumni can interact more with students on campus, and so I'm open to any ideas folks have, and also I think I will be, in a much more systematic way, having conversations with groups of alumni, just like I've done the internal listening tour. It's time to do the alumni listening tour.
Yeah, so, excuse me. I just say inviting the alumni community to contact you is an invitation to overflowing your inbox, because this is a passionate and engaged crowd.
It's
so
true,
you may be
true.
hearing from 145,000 of us. So, for those of us who have either just graduated from MIT or maybe a few decades ago, we know that there's a pride and power in the individuality of MIT's schools and departments and labs and centers. How do you square that decentralized approach with the need to unite the campus across disciplines and specifically to address climate change?
I think, that tension definitely exists here. When I ask, is there a center on X, Y, or Z at MIT, whatever it is, and I look it up, the answer is there's like 8 of them or 10 of them. And sometimes they don't even know the other ones exist. And so, I think one thing that's important as we move forward on some of the big problems, societal problems like climate change, like the impact of AI on our work environment and on our personal environment, we're going to really have to think about, again, how we harness the collective. We also have to think about what things are better done in a central way and what things are better done in a decentralized manner. So, for instance, I hear a lot about tools for better research administration, et cetera. There's no reason for every little unit to be deploying that to reach goals. So we have to think what centralized services look like, what's deployed well in a central fashion. And also, part of it, as I mentioned, and I think this is true for climate change, but across the board, is that, historically, MIT has had a huge impact based on the work of individual brilliant scientists, engineers, et cetera. Now I think that society's problems demand more collective action. It takes many, many, many different approaches to tackle these problems. And this is not only science and engineering, this is the humanities, this is social sciences. So for many of these large societal problems, I think that the role of the central administration is going to be to take sort of a bird's eye view across the whole landscape and try to help make the kind of connections that are needed to look at these problems holistically.
Great. So just on that note about decentralization, I recall one of my predecessors, Don Schober, saying, if there's a good idea, then there's already 12 people, 12 different organizations at MIT doing it.
Exactly,
So,
exactly. That has definitely been my experience. That's part of that fire hose you talked about.
Right, right. So beyond climate change, you just mentioned AI.
Yes.
What other pressing societal changes or challenges do you think there are that the MIT community needs to tackle during your presidency?
Yeah, and I'll make one comment about AI. I think that MIT has been at the forefront of technological innovation in terms of AI, but it also has a strong presence in terms of thinking about the social and ethical consequences of AI. And so I think that we have to step up our game in terms of all of the arenas where we're sort of the trusted guarantors of a lot of the technology being developed that is going to really impact the broader world. And from recent external surveys, it's been clear that the broader public trusts MIT to deploy technology responsibly. And I think that has to be part of our conversation. So that's one concern I have, and not just about AI, but really about anything we do. Another thing that's near and dear to my heart is, the role of the life sciences at MIT and also in terms of biomedical innovation. And I think MIT is almost unique in the very close juxtaposition of the life sciences and innovation in engineering. And also, obviously, we're situated geographically due to a lot of the efforts of MIT people over the many years to one of the most vibrant biotech and biomedical innovation hubs in the world. And so I think it behooves MIT to address the many, many biomedical challenges that face us. I mean, I think we most recently came through the pandemic and saw how important it was, efforts at MIT and efforts in the broader Cambridge area to combat the pandemic. And I think MIT has to stay on the top of its game for emerging infectious disease, for other health challenges. And that's something that I really want to think again about how to build the collective, because every corner of MIT has somebody working on some aspects of the life sciences or biomedical sciences.
So in short, I would say you have the inbox from hell. You've talked about your belief in the theory of incrementalism, not only in the theory of incrementalism, but in the theory of rapid incrementalism.
Yeah.
Can you enlighten us about that?
Yeah, people would always ask me, what my theory of sort of management and change was. And I always thought back to how I did experiments in the lab and how I wrote grants. When you write grants and you want to get funding, you've got to really be looking down the road to your goals, whether it be 5 years from then or 10 years from then. You have to articulate big important ideas. No one wants to give you money for like your next experiment. But the truth is, the way scientists do work is they keep that long goal in mind, but you have to be always integrating the data that you're receiving and reacting. And if you're good, you're reacting rapidly. You're incorporating the information you're getting. You're changing direction somewhat. You still may have that long goal down the road, but you've got to be able to rapidly make very incremental adjustments in your course. And people always used to ask me, even when I was provost, and I've certainly heard this all the time as president, what's your vision? And I can articulate some really long-term vision, but I've got to think in concrete ways how we get there. And how we get there is plotting your course, getting data input, and also, by the way, having a strong team, having them doing their things and bring back what they're doing to, again, allow you to adjust your course. So I've always thought that, the successful academic administrator takes in that information and, honestly, if you move at like what people sometimes call glacial academic pace, you're not going to get there. So that's where the rapid comes in, to make quick changes and adapt.
Yeah, so it's interesting. I think in the presentations we saw this morning, there was definitely some of that, the mentioning about, well, okay, it didn't work, so now we got to change and try something else. Although I guess in space exploration, it does happen at a little bit slower pace, perhaps.
Yeah.
But, okay. So how do you think that the MIT alumni community can help you as you confront these challenges and opportunities?
Right. I mean, one thing I already mentioned in terms of just on the ground, grassroots action in things like climate change, et cetera. I think another thing is that two other things. One has to do with the interactions with students on campus now. I was actually surprised, and again, this is not unique to MIT, but it is an issue, which is in surveys of our students, only 30 to 40% of students will say that they have robust, significant interactions with faculty outside the classroom. And I think that is happening because everyone is so incredibly busy. Everyone is really engaged in and immersed in their work. But I think the students are crying for, if you will, they might not admit it, but they're crying for an adult presence sometimes, and interactions, guidance in terms of what their future careers will look like, in terms of how they navigate the MIT of today with respect to how some of their predecessors navigated MIT. And I think we could think much more intentionally about how we have really strong interactions between alumni and the current students. Now, I think there's another issue on the horizon. I think people are probably aware that the Supreme Court is likely to come down with a decision fairly soon, and not to get totally ahead of it, I anticipate, and if you read the newspapers, most people anticipate that they will be striking down affirmative action as we understand it right now in college admissions. And as we understand it right now is, a checkbox on an application. And I think MIT has become such a rich and diverse community, and that sort of diversity enhances the community life, it enhances the science, it enhances the engineering on campus, and it actually prepares our students, all of our students, for what life is going to be like out in the real world. And I think the alumni are really going to have to be ambassadors to making sure that our outreach and access is really broad, that the pipeline to MIT stays wide, and that we can select the very best talent no matter where people are from, no matter their demographic, diversity, et cetera. And I think it's going to behoove us as a large community to try to keep this community diverse and vibrant. And if you look at MIT over the years, it's never, ever been stronger academically, and it's never, ever been more diverse.
Yes, it's true. And I will say, I think you will find willing partners in the alumni community on both those efforts. The mentoring piece, I know that we have mentoring programs, and a lot of alumni have stepped forward and have said they have been disappointed that they have not yet been contacted. So maybe there's more we can do there. And certainly the assistance with making sure that we continue to attract the world's best students from everywhere. So moving from a kind of global view to a little closer to home, specifically your new home here on campus. This has been an interesting year for MIT, that it simultaneously completed two major efforts: the publication of the Strategic Action Plan for Belonging, Achievement, and Composition, as well as the faculty statement on freedom of expression. Some alumni have questioned how those two efforts can coexist, feel that maybe that they're in conflict with one another. I know you have said that they can and should. Would you like to share your thoughts on that philosophy and a little more on that?
Absolutely. I'm glad you're hitting me these softballs, Steve. This is
softball questions.
This is a complicated question. So, I really do believe that that the notion of, belonging, achievement, and composition, and the notion of freedom of expression, I think it's a false dichotomy. I really do not see that we cannot have an inclusive, welcoming, diverse environment while still allowing people or encouraging people to say what's on their minds. Now, the devil's in the details there, and probably many of you saw the video that I released in the wake of some of the freedom of expression issues emerging on campus. And one thing I said there, I really believe strongly, which is there is a distinction between what you can say and what you should say. And so, part of it is going to be really, as I mentioned, coming out of the pandemic in particular, really building community, in a sense, immunizing ourselves against, you know, the sort of hate speech that really does provoke people in terms of thinking about that dichotomy. So I think that's part of it. The other thing is to think a little bit more about time, manner, and place of expression. So, for example, we want it to be an environment for learning and for work that people feel comfortable, happy being here. I could argue that seeing hateful statements posted along the infinite is not the right time, manner, or place to achieve that. And so you can put in, and we are working on policies around this, you can put in policies that help provide guardrails without violating people's fundamental right to expression. The final thing I'll say about this is that I see a clear distinction between espousing your beliefs on something in general and targeting individuals, particularly vulnerable individuals in the community, students, et cetera. To me, there's no world in which that is really acceptable and is not really part of how we understand free speech on campus. So finally, and I say finally, I'll say on this one more point, you know, we're working hard to encourage a lot more dialogue on these issues on campus, and I think, you know, part of the issue across American life at this point is really polarization, and the more that we can bring people into conversation together, the less problem we're going to have with those flashpoints. And the thing about students is you can call a symposium on anything you want, and it will be filled with faculty and staff and community members, and students aren't always volunteering to attend what they think is of an extra class. And so I think we're going to have to work hard, and I know, you know, Susie Nelson and Melissa Nobles and Ian Waits and others are thinking a lot about this, which is how do you bring these conversations to the dorms, to the places where students hang out and live, and how do you craft, if you will, sort of case studies and discussions that are relevant to them?
Yeah. I'm reminded, I know that John Dozier has started a symposium series, Dialogues Across Differences. I was able to attend the first one with you, and I think it's an interesting subject. It's a challenge for our time, not only because of the polarization, that larger societal polarization is beginning to seep into the academy as well.
Exactly.
So yeah, that's a softball question. So hopefully moving to one that's perhaps, oh no, this is also not a softball question. Another area of campus interest. Some in the audience today might know about the establishment of the Graduate Student Union here at MIT, and that there have been ongoing negotiations between the union and the administration, and those predate your arrival, but they're continuing. Knowing that there are sensitive conversations and there are things you may not be able to share with us, can you provide us with like a top-level view of what's happening now and how you foresee the relationship with the Graduate Student Union going forward?
Yeah, thank you. You know, first of all, I should say, again, this is not unique to MIT. It's really a national movement among graduate students at many, many universities unionizing. You know, I think the negotiations have been between the graduate students and the sort of administration slash faculty side of things have been really cordial, really productive, and despite the narrative that we hear, I think, you know, we're quite a long way to an agreement, meaning that there are many, many, many issues that have been resolved. Now, part of the issue now is we're at the sticking point on a couple things. One has to do with, as you might anticipate, financial arrangements and pay. So, you know, students asked for initially a 30% increase. They had a substantial increase last year before I arrived, and MIT graduate students are already the second highest paid in the country. So, you know, there's not a lot of headroom there. We're trying to work with them productively. But I would say the main sticking point at this point is what we would call a distinction between an open and a closed union shop. So a closed shop or a union shop means that all of the students that are technically in the bargaining unit have got to join the union, pay dues to the union, and that's, you know, around $700 a year, which out of a graduate student stipend is significant. And that money goes to the national union. So whether it be here, you know, electrical workers, my old institution, you know, they were trying to organize around service workers. The United Auto Workers Union is in this game as well. But they're interested in bringing new individuals into the union. Obviously, there has to be a revenue associated with it. And we believe that students, even if the union passed, first of all, a lot of the students didn't vote. And second of all, even those that did vote, there were plenty of students who did not vote for the union. And so we believe that students should elect to either join or not join the union, pay dues or not pay dues. The issue, though, obviously, is, and they're in close consultation with the national union. The national union wants, obviously a closed shop. Now, there may be compromise points. So, for instance, there's something called an agency shop, which would mandate that student pay fees, but pay these dues, but it doesn't have to go to the union. It could go, for instance, into a student hardship fund. There are other ways to arrange this, and we're really in a lot of conversation, but we would like, if we can, to come out of this negotiation preserving the right for students to choose to participate or not in the union, but we'll see how it goes. As I said, I think the channels of communications are open, and the students and the negotiators have had many good conversations, and hopefully we are reaching a point where we can wind this up.
Great. Just a very quick follow-up on that. Do you have any thoughts about the time frame for that, or do you feel like you can't say at this time?
It's hard to say because the students had originally put out some information to their sort of stakeholders saying they wanted to get it done before commencement, but obviously that didn't happen. And so, part of that obviously is that some students who are involved in the union are graduating. So my guess is that there's going to have to be a little bit of regrouping. Hopefully over the summer. Look, I'd like to have this settled when we start in the fall, but and I'm generally an optimist by nature, so I'm hopeful.
Great, great. Well, we look forward to seeing that resolved in a way that is satisfactory to everyone's interests. So now, how about a few softball questions?
Okay.
These are the softball questions.
Okay.
We've talked about your role as MIT leader and the inbox from hell and all of that. I think our alumni might like to know a little bit about you as a person. So I'm going to ask you what we'll call a lightning round of questions about getting to know Sally as a person. Are you a morning person or a night owl?
Night, but I don't have a choice nowadays. But intrinsically, I'm a night person.
Okay. Dogs or cats?
Dogs.
Well, that
Did
was
I wait
definite.
long enough?
Okay, how about large dogs or small dogs?
Oh yeah, this is a hard one. For those of you who see me walking around campus, I have a Collie Shepherd mix and a Chihuahua mix. So, that's like asking, which one of your children do you like better, except they don't really understand the answer, but yeah.
And by the way, you just lost my 2 cats vote.
There you go.
Okay, do you prefer for a vacation the mountains or a beach?
Mountains.
Okay. And do you have a favorite MIT alum in pop culture?
Oh, this may be showing my age, but it's, Will Hunting, as opposed to I haven't even seen some of the more recent movies.
So good Will Hunting, okay. And how about a favorite book or movie about MIT?
Favorite book or a movie about MIT? Isn't Good Will Hunting?
Okay, well, are you allowed to answer the same question?
Yeah, I think so.
Okay. And last, if you were trapped on a desert island and you could only have one record album with you, what record would you take?
Oh, definitely James Taylor's Greatest Hits.
Okay.
I'm like a huge James Taylor fan.
There you go.
I'm in the right state now.
So, knowing that you moved up here from North Carolina to Massachusetts, I don't need to ask you to rate your experience about the weather.
True.
Or the pollen, I might say. But what are some of the things that you've learned about living here in Cambridge and the on-campus that you're enjoying so far?
Well, I have to say that, Cambridge and Boston in general have great food. So I've really enjoyed, a much expanded restaurant scene. And even I have to say, all the food all the food at meetings and alumni, everything, haven't had a bad meal since I arrived here. So that's been great. I really like living right along the river. It's just fantastic every day to look out and see people rowing and sailing. In fact, I told my husband that I was you have to go take sailing lessons so that we can go sailing. So he's like, I like how that, I have to, anyway. So I'm hoping that will happen. And you know, it's a great place to just walk around. I mean, really enjoying walking the dogs all over Cambridge and Boston, and so it's been fun all around. And the weather recently has been wonderful.
Great, great. Although unfortunately not today.
Not today, but
so,
in general.
We're out of time, but I would like to get to one final question. Of course, it may not be quick, fast, but we'll do our best. What are the early messages that you would like to share with our alumni about the direction of MIT under your leadership?
Yeah, I mean, I think that a couple things. First of all, MIT has always been this beacon for the best talent in the world, and the most important thing I can do is to sustain that and to continue to build on that. And so I think, you know, we have to keep, as I said, our sort of pipeline of talent broad, but also just, you know, get the MIT message out to the world and continue to bring the best and brightest at all levels, from, you know, undergrads to graduate students to faculty to staff, et cetera. The other thing is, you know, what attracted me to MIT in the first place, I mean, I've said in other settings, you know, I was perfectly happy where I was. It wasn't that I woke up every morning and said, I gotta go be a president somewhere. But, you know, when MIT called, I couldn't say no, because I think the most important thing is that MIT is maybe the place, or at least one of the very few places, that can address in an effective way the many challenges facing us in society. And I think that, to me, the most important thing is to continue the impact of MIT on the broader world. And honestly, as an administrator, to do everything I can to grease the skids to enable MIT to achieve those heights.
Wonderful. Thank you, President Kornbluth, very much for joining us this morning for Tech Day. Before we conclude Tech Day, I'd like to bring it back to our earlier discussion on space, and we have a unique presentation, a gift for you.
Okay.
In a moment, we will bring to the stage Dr. Maya Nasser, but first a little bit about Maya. Maya is a triple-degreed MIT Aeroastro alum, having earned her PhD just this week. Congratulations to Dr. Maya. Dr. Nasser. She is also the project lead and co-founder of HUMANS, which is an acronym that stands for Humanity United with MIT Art and Nanotechnology in Space. Everybody got that? HUMANS. Somebody worked hard on that one. This MIT project combines art and nanotechnology for increasing global representation in space, and has done so by creating a 6-inch silicon wafer using MIT nanotechnology that contains a recording of messages in 64 languages from people from more than 80 countries around the world. This nanowafer just traveled to the International Space Station, where astronauts will display the HUMANS wafer and the audio submissions in a live stream, allowing contributors to hear their own voices, and for some, their native languages in space for the very first time. President Kornbluth, Maya would like to present to you an exact replica of the HUMANS nanowafer. Come on up, Maya.
So much. Of course. Oh, fantastic. This is also something I haven't had in my life before. Thank you so much. Fantastic. Wow, that's amazing.
Do you want to say thank you?
Oh, yeah. Okay. Well, I'll just thank everyone here. Thank you, Steve. Thanks, Whitney, and thanks to the hundreds of volunteers that have made this all possible. And thanks for joining us for my very first Tech Day. And I hope you enjoy the rest of your time on campus.
Thank you so much.
Thank you.
Wow, we're on our way to lunch. So very briefly, I don't want to keep you between you and lunch. I just want to take a moment to thank our presenters today. President Sally Kornbluth, Vice President Maria Zuber, Alumni Association CEO Whitney Espich, Professors Cahoy, Wood, Perron, and Kerri, and our Better World Service Award winners, Vanessa, Segun, and Don, and Maya Nasser and the Humans team, and of course all of the Alumni Association staff. Thank you for being here with us today, and if you're attending the Tech Reunions picnic, it's right outside. So enjoy the rest of your weekend. Have a great afternoon. Thank you.